Hello everyone. Our topic for today is single phase full wave controlled rectifier. Last time we took single phase full wave uncontrolled rectifier. This time we will be using controlled, which is, we call it thyristor or SCR, which is silicon controlled rectifier. Let's see what will happen here, since everything is almost ready for us. To minimize the time of the video. This is the bridge with 4 thyristors, and let's see what will happen if this is the V source. This is the V source right here. This is positive and this is negative. Let's put the positive with the red color and see what will happen. So the positive will go here, same as what we have done before. So this thyristor right here, or SCR, will be conducting the first one. So we will call it thyristor 1. And then the current will go, it cannot go down. It will go to the load from this direction right here. You see the direction? Because this one here, this is V out. This is V out DC, which is across the resistance, and this is positive and this is negative. So the current will come to the load from the positive direction. This point is very important to know why this is full wave controlled rectifier. Then the current will come back through this or through this. It cannot go through this because this here will be positive and this will be an open circuit, so it will come through this. So this thyristor here will be thyristor number 2, and then the circuit will be closed. We will name the thyristors, or the SCR, silicon controlled rectifier, according to the sequence. So this one was conducted number, the first one, so we will call it thyristor number 1, and this one conducted number, the second one, so we will call it thyristor number 2. And then for the negative, we're going to use the black color, so you can see this is the negative. So the negative will start from here. This is the negative here, and this was the positive. So the negative will go here. Cannot go down, of course. It's going up because the thyristor is same as power diode, just one-way path. So this one here will be thyristor number 3 because it's conducted in sequence the third one. Then the current will come to the load from the positive direction. So both currents, the positive and the negative, goes to the load from the same direction. That's why we will see everything in the positive side. Then current, it cannot come here because this one here will be charged and this will be an open circuit. So it will come here. So this one here is thyristor number 4, and then the circuit will be closed. That's the flow of the current for the positive and negative. Let's see here, let's draw the V out. In the power diode, this is my V out. This here positive. Okay. This is here positive. And then here, this is also like this. As I told you, why everything in the positive? We just drove 1 cycle and a half. This is 1T here, from here up to here. This 1T, and we will draw 1.5 is enough. And this is here. Okay. So everything in the positive side, because the current goes to the load from the positive side. So what we have done here, the positive came to the load from the positive, and then we open a path for the negative current. We open a path for the negative current to come to the load from the positive side. And everything appears in the positive side, and that's a DC now. This is a DC. Is it a good DC? Not yet, because we still have ripples. that's why it's not a good DC. But it's a DC since the polarity is positive. Okay, so this one here is for the uncontrolled or for the controlled if alpha is 0. So if alpha is 0, this is my output. So if alpha is 0, then uncontrolled will be same as controlled. But what's the good thing about controlled? We can play with the alpha, which is the firing angle. Okay. So let's choose, firing angle. From before we decide that this is 30 here degrees, and this is 60 degrees, and this is 90 degrees right here, and this is 120 degrees, and this is 150 degrees, and this is 180 degrees, which is pi. Okay? And this is here 270 degrees, and this is 360 degrees, which is 1 pi. This is here 1 pi. Sorry, 2 pi, and this is here pi. Okay? So now let's choose a firing angle. We can choose anything. We can choose 30, we can choose 60, 90, whatever. But let's choose, for the time being, let's choose 60 and see what's going on here. Okay, so if alpha is 60 here, so I'm going to choose alpha to be 60 degrees. So means that before 60, I have nothing. I did not start yet. So this will be 0. From 0 to 60, nothing. And then from 0, I will start. I will start firing. So I will start my pulse. Then when it comes here, this will be all 0 here. This will be all 0 here, and then I will start. So this will be gone. Same thing from here up to here, and this is. That's if the alpha is 60. If the alpha is 90, it's the same. I will come from here. This will be all 0. If the alpha is 90, I will come from here, and this is all 0, so this will disappear. And I will only see half of the pulse. Okay, so let's leave it 60 for the time being. And let's see the current also. The current is, it follows the voltage. It's the same as the volt, but the peak is less. So that's the current right here. That's the current right here. And that's the current right here. So it will be the same. This will be 0 here. No current since there is no voltage. And this is my output here. And same thing right here. And then same thing right here, guys. So this is my V out, DC, and this is, the red one is my I out, DC. Black is V out, and the red is I out. Almost the same as uncontrolled as what we have done before, but this is controlled, so we can play with the firing angle. We can start from 30, we can start from 45, we can start from 60, and so on. Now this is for the resistive load only, guys. So that's, we did not see a ripple. We have no ripple, because when we have inductive load, we will have a ripple. Unless firing angle is 0, then we will have no ripple, because there is no time for the ripple. There is no time for the inductive to release. So we will see no ripple if alpha is 0. Otherwise, if alpha is bigger than 0, we're going to see a ripple. Okay, let's see V thyristor. V thyristor is the voltage across the thyristor. Anyone. You can choose V thyristor, this one here, which is V thyristor 1. So what will be the voltage across thyristor 1? We know that the current is the same here and here. So the voltage, when there is a current, the voltage across the thyristor is 0, as we agreed before. So means that from this point here to this point, the current is 0. Now what's this? Which one? Which diode is this? We have to know first. This one here is V. Sorry, is thyristor here. This is here thyristor. 1 and 2. And this one here is thyristor 3 and 4. And this one here is thyristor 1 and 2. Okay. So if we look at the voltage across this thyristor, we look at the current. When there is current, voltage across this thyristor is 0 because it's like a short circuit. So the potential difference is 0. So means this is thyristor 1 and 2. The voltage across the thyristor here, voltage across thyristor 1. Let me just rewrite this. Voltage across thyristor 1, 2. Okay, it will be here 0. This one we don't look at that, and also it will be 0 right here. So 0 right here. Okay. What else? This one here, there will be a voltage. There will be a voltage right here, so that's the voltage in the negative. Okay, so that you will see this. And you will see the rest. The rest, how to see the rest? You just draw everything. And we know this from here. We erase this, and that's the rest. We'll see this. Same thing here, you will draw everything just to see what's going on. And this one here is 0 up to here. So this will be erased. That's what you will see. This is V thyristor across 1 and 2. It will be the same. Even if I come here and draw V thyristor 2, this one is the same as this one because they have the same current. Okay, so this one here is for resistive load only. Okay, this is for resistive load only. Now, if we add a inductive, if we just add inductive here, if we add inductive, okay, RL now. Now we have RL. What will change? Let's look at V out, I out, and we will see. First we have to know, is the inductive huge or small? Because it depends. If the inductive is huge, means the ripple will be big. If the inductive is tiny, small, the ripple will be small, as we explained before. So let's see here. V out. I normally use the black for the V out. So the V out now, I will draw everything, and I will draw here and see. Okay. I will draw everything and see. I will draw here the poles and see what's going on. This is same as the arm control. Then I will see, okay, I will ask myself, what's my firing angle? Let's use the same, which is 60. So alpha equals 60, no change. Okay. Okay, no problem. We can see something right here. Because we're looking for discontinuous current. And for that, we need to, okay, for discontinuous current, alpha has to be big. Where inductive load is small. So let's choose 90 degrees. Okay, 90. It can be, by the way, it can be 60, and also it's discontinuous. Let's use 60. Let's keep it the same. 60 degrees here or 90 degrees, whatever. It depends. If the inductive load is small, and the alpha is big, then we will have a discontinuous current. But if the inductive is huge, so we will have the the ripple, the negative ripple will be long, and the alpha is small, then we will have continuous current. We will see that. Okay, let's assume the same, which is 60. So 60 means here. Okay? 60 means here. 60 means here. So this will be my output, same as before, no change. But now we have inductive, guys. We have inductive right here, RL. So I will have negative ripple. Let's assume that that inductive load is small enough. That's, we're going to use this word enough. Okay? Let's assume here that alpha inductive is small enough, so we will say that. Let me use the red, guys. I think it's better for me. Here, alpha is 60 degrees, which is big enough, where inductive is small enough. Let's see. Okay, so now the negative ripple should be like this. It should look like this. That's from the resource. But if the inductive is small enough, I will assume it's here. It's not. Okay? I will assume, if I draw everything here, that it's here. Okay? And there is a distance which is when the inductive stops and when the alpha starts. So there is a gap. That's why we will have a discontinuous current. You see the gap right here? The inductive finished or released very fast and stops, and then the alpha starts after a time. So we will have a gap. Okay, same thing here. This will be from the previous one right here. It will be like this. And that's a gap. Now let's see the current. The current, as what we have seen before, this is the gap, same one here. But it will be, now it will not stop here. It will stop here, we know this. It will go like this. Actually, it will, I mean, if you look at it, I mean, I want you just to look in your textbook, guys, in page 131, 132, and 1. Yeah, that's for the, 133, that's for the resistive load only. And you will see that in page 132, the draw. But for the inductive, you will see it in page 134. And also in your notes, you can look in page 49 and 50. That's for the resistive load only. And then you can look at page 51 and 52 and 53 and 54. That's for the inductive loads for both cases, because we're going to have two cases. Okay, let's see here. So the current, as what we have done on the control, the same. It will start now from 0 here, and it will stop here, guys. It starts here, not the same as the resistive because of the inductive. Okay, so that's my output. It stops here, and then at this point right here, it's 0. Then it will start again, and then 0, and then it will start again, and so on. So that's why we call this one discontinuous. Alpha is 60, big enough. For us, big enough. Even if it's here, if it's less than 60, if it starts from here, it's still big enough. The main thing that when we say big enough and small enough means they don't touch each other. The 60 here, it can be small enough in some cases. It can be small enough. We will see that in the continuous. Okay, so this one here, I mean, you can draw the that's the Venus. Okay. Let's take another case. Which is, let's say that I'm saying for the discontinuous, case. Let's say the alpha is 90. Or the alpha is 120. Okay. And where inductive load is small enough. Small enough in this case means it stops before the 120 degrees. It could be bigger than this. So let's see here. Can draw the black, which is the V out. The V out starts here. Okay. That's my V out. Okay. And that's my V out here. And that's my V out here. Okay, though, so we said 120 degrees. We know that this is 90 degrees here, and this is 120 degrees. So it will start right here. Okay, so this is gone. And it will start right here, 120 degrees. And it will start right here, and this will be gone. Wow. Let's say that the current is, I mean, the inductive is huge, but still is huge. It's bigger than this. It's huge in this case, but still small enough because it did not reach the 120 degrees. Let's look at that. Okay, if I go ahead and just draw this, this is my negative. Okay. Now let's see here. So now my inductive just release. It's bigger than this, guys. Release, up to here, up to 90 degrees. Okay. See that small, your inductive, I mean small as a base, where L is small enough. See here, this inductive is bigger than this, but still small enough because it did not reach that point. Let's see here. This is my here. I'm following the V source, guys. Okay. So now it will go here. It will reach up to this 90 degrees here. Okay, so this is gone. Yeah, the ripple is big. The inductive is huge, but still is not enough to reach that point. Okay, following the here, so it will reach here, this point, and the rest is zero. You guys see that? Now let's look at the current. Okay, the current will be zero here, guys, because they did not touch each other. I mean the alpha. I mean the inductive stops here, where the alpha did not start yet, and then we will have the current. It will start here, and it will end up at this point. Then here is zero, guys, because the release of the inductive stops, finished, done, and the firing angle did not start yet. And if the firing angle is not fired yet, we'll have no current. And then we will have a current here, and this is zero right here, and then I will have something like that. And same thing here. Something like this. This is both cases, guys. For two alphas and for two difference, but that's what we say big enough. This one was 60 degrees, and it was big enough. This one was 80 degrees, means still this is big enough. That's why we use the word enough. Okay, let's Let's look at this case right here, which is a continuous current. This is our case here, continuous current. In this case, which is continuous current, it will be the opposite. So we will say that alpha is small enough where inductive is big enough. I can use the two cases, same cases, 60 for example. Okay, I will draw, but I should raise this a little bit. Okay. I should say that here, alpha is small enough where inductive is big enough. Okay, let's see here. This case, guys, we have RL, but it's continuous current. Okay, the current will be continuous. Here it's discontinuous. You guys see here discontinuous for two different cases. Let's see here. This is the V source. Okay. I'm going to use the blue. You know, the blue for the V source. This is the V source, guys, which is same as this. We're going to follow this. This is the V source. Okay, V out here. So this one here is V out, DC, and I out, DC. Okay, and let's look at this for the same case, for the same alpha, okay, which is alpha equals 60 degrees. So we consider that this one is small enough. Here it was big enough, but now the inductive will be big. So here, okay, that's my output V out. Same as the V out with uncontrolled rectifier as before. But now I will start the firing angle from here, 60. So this is 0 right here. So this is my 60 right here. This is my 60. Same as this. But now the inductive is big. Now the inductive is big. You see here the inductive was small, so it stops before. But now no. My inductive, so I'm going to draw this one here. Okay. See here? I'm going to draw all the negative, so I can draw. That's my. Okay. So the inductive is big. So let's assume that the inductive stops here. It's big. It's bigger than before. See here? Or I can say it's bigger where it stops after, for example. Okay? It can stop here. For example, it stops here. Okay? It could be here, it could be there, it doesn't matter. Okay, but let's say, okay. And for the best, for the good drawing, I'm gonna say it stops here. So I don't want to confuse you. Because you're not gonna see the rest. I mean, you're not gonna see, if it's more than this, if the inductive is bigger than this, you're not gonna see that. Because if the firing angle starts, the inductive will not release. We will have another cycle. Okay? That's why here we don't see a negative ripple. I mean, especially if we have alpha equals to 0, we don't see negative ripple, even if the inductive is big, because the next one will start immediately. So you're not going to see the inductive ripple. So here, same thing. Even if the inductive is big, you're not going to see nothing here, because now the firing angle starts. So this is gone. So even if it's bigger, you're not going to see it. Up to here. This is gone, and this is gone here. This will be my V out, and let's look at the current. The current will be continuous. So it will come from here like this, and then it was continuous from here. Okay. Something case, which is if alpha is 60 here and inductive is big enough. Enough means it reaches the firing end. If we have another case, which is same as 120, let's say 120. Okay, so 120, I will have the same right here. I will draw everything as before. Let me just draw it from here next. Okay. Okay. And then 120, we said it will be right here, 120. This is 90 degrees here. And this is 120. So 120 is here, so this is gone. 120 is here, so this is gone. 120 is here, so this is gone. But now the inductive is huge, okay? So the inductive is huge, so it will reach. Let's draw the negative here. Okay? So let's draw the negative here, so I can see what's going on, what will happen with the inductive. Let's draw the negative here. I'm following the results, guys. Okay? So the inductive will be going up to this point here, and it will stop. You see that? Same thing here, it will go, and it will stop here, because now the firing angle will start. Okay? Okay. So here, and now, it's up there, I'm sorry. Sorry. Now let's look at the current. Current, we said it will be continuous because there is no gap. Okay? So if I start from here, it will be like this. You see here? Okay? Something like this. Okay? So this case here, alpha is 120 degrees. Alpha is 120 degrees, where inductive is big enough. Okay? Okay, you can see this one here, which is if alpha is greater than 90, Vmax is absent. Okay? You see here, we have no Vmax, because Vmax is this point. Now we have no Vmax. Same thing here. Okay, Vmax should be here, it's gone. And the phase shift angle between thyristor 1 and thyristor 3 is 180 degrees, yes. Because this is thyristor 1 and thyristor 2, they start from 0, so the phase shift is 0. But between this and this is 180 degrees. Okay? Those are the equations. Those are the main equations that you need to know. This is the V out for the resistive load only, which is Vmax over pi, 1 plus cosine alpha. This is for the resistive load only. And this is the IRMS for also the resistive load only. You will have, I want you just to look to the equations in your notes. You will see the equation for the resistive load in page 50, please. Okay, V out. And you're going to see the equations for the resistive load and inductive load in pages 52 and 54. And also you can look at your textbook in pages 132 for the equations, and also in page 136 for the inductive and resistive. We have two cases, continuous and discontinuous. This is a discontinuous current, guys. And if the case is discontinuous current, you're going to use this equation here. So if I give you an example and you find out that it's discontinuous, then you need to, or if I tell you in the example, this is a discontinuous case, then you need to find this V out equation. V out, DC V max over pi cosine alpha minus cosine beta. This is for the R load discontinuous. So you're going to use this and then use Ohm's law, which is I equals V out over resistance and power. P out DC equals I out DC times V out DC. And for the absorbed power, P out RMS equals I out RMS times V out RMS, and so on. Same as what we have done before in Uncle. And then the other case, which is continuous current, this case right here, we're going to use this continuous current, and the V out DC equals 2V max over pi cosine alpha. So those are the two cases. Let's look at example 4-6 in page 133. Okay, this is the example right here. Okay, this is example 4-6. Look at it, please. The V source is 120. The resistance is 20 ohm, the frequency is 60 hertz, and we have a firing angle of 40 degrees. It says determine the average current in the load, the power absorbed by the load, and the source volt ampere. Okay, this example is in your textbook on page 133. So which case we're going to use right here? Which case from those cases? Do we see inductive here? So we have no inductive. So this is our case, the first case. So now, what would be the V out? V out DC equals V max over pi 1 plus cosine alpha. We have everything. Do we have V max? V out equals V max over pi 1 plus cosine alpha. Now we need Vmax. How to find Vmax, guys? We have done this before. Okay? And the Vmax is the V source times square root of 2. So this one right here. So Vmax equals 120 times square root of 2. So you do the calculation, and V out will be this value right here, 120 times square root of 2. So it will be, I think, around, I don't know, 160 something or 140 something. And then the answer will be 94.5 volts. This is my V out DC. And then I out, determine the average current in the load. Now you find the average current. So I out equals V out, which is this value, V out DC, over resistance, and the V out here is 94.5 divided by 20 equals 4.77 ampere. 4.77 ampere. As I told you, it's in page 133. Okay. Then they want you to find IRMS, which is this equation right here. So I out RMS. You use this equation right here, and the answer will be 5.8. But I want you to look at this here in your text. When you do the equation right here, because you have degrees, I mean, you need to make sure about your calculator. Make sure that it's in radians, and you convert this one here into radians. Okay? You convert this into radians. You have to work either with radians or degrees. What my advice? Put your calculator in radians and work with radians. Okay? So if you have a degrees, 40 degrees converted into radians, then you know how to do this, how to convert from radians into degrees. Otherwise, you will have an issue with your answer. Okay? You cannot just mix up between radian values and degrees. So put your calculator in radians, and then put the For example, this is 40, this is 40, put it radians, convert it to radians, and you will be okay in this case. I mean, the 40, it's the 40 degrees, where's the 40 degrees here? In radians, it's 0.698. That's in radian, okay? Radians. So just convert this into radians, put your calculator into in radian mode, and you will be okay. Okay, then the power, which is P, to find the power, guys, P out equals I out RMS squared times voltage. Okay? Sorry, times resistance. Okay, so you have the P out RMS, you have the I out RMS, which is this value right here, this value right here, and you have the resistance, which is 120, so the power would be 673 watts. 673 watts. Okay, then the apparent power, which is S. S equals V RMS times I RMS, and we have everything right here. Just multiply the V RMS, which is the 120, times the I RMS, which is 5.8, and you will get 696 volt ampere. 696 volt ampere, and the power factor is the real power, okay? Real power, which we found first. This one here, real power over the apparent power. So that's the power factor here, which is 673 divided by 696. And it's 0.967, which is perfect. Okay, this is for full wave bridge uncontrolled rectifier single phase. That's it, guys. See you next time.